So I'm very happy to be here today, and would also like to thank workshop organizers for inviting me to be part of this event. All right, so let me get started. So I will be talking about non-invasive physiological monitoring. So this is the research area that I have been in for over the last 2 decades. It's been a very long time. And initially we focused on health applications, but over the last, I would say about 7 or 8 years, we have started looking into applications in smart buildings and energy efficiency. And I will focus most of my talk on those topics today. So I'm a professor of electrical engineering in the Department of Electrical and Computer Engineering at UH Manoa. We're about 2 miles inland from Waikiki. And I invite you all to come and visit. Our governor has officially welcomed visitors to Hawaii. So we hope to be going back to closer to normal. I don't think we'll ever be back to life as we knew it, but hopefully to something a little more normal. So the work, let's see, it looks like I'm having trouble with changing my slides for some reason. Hold on. There we go. So this is the work that I have been working on with my husband, Boric-Lubecke, for, as I mentioned, over 2 decades. So I will introduce both of us at the same time. We're both professors at University of Hawaii. We both have masters from Caltech, which is where we met. And I got a PhD from UCLA, Victor got a PhD from Caltech. Then we spent time at NASA JPL, in RIKEN, in Japan, and at Luce and Bell Labs before joining University of Hawaii. Should I be monitoring the chat? No, okay. All right. I'm sorry, it seems like it's a little bit slow when I change. When I go forward, it looks like my slides got stuck. There we go. So I will tell you about our research work, but I also want to say a little bit about our tech transfer efforts. So we have spun off 2 startup companies, First Cry Medical, focused on health applications, and then AdNovive, which is currently commercialized this technology for smart buildings. So what we do is radio wave Doppler radar. And the basic idea here is when you send a wave of any kind, for that matter, the same thing happens with an acoustic wave and radio wave and with a light wave towards any object that is moving, that wave is going to be modulated by the motion that it encounters. And if you're able to receive the reflected wave and process it properly, you can extract a lot of interesting information. So if the waves bounce off of people, that received signal is going to carry very interesting cardiopulmonary information. And that's essentially what we have been focusing on. So the radar can be implemented in many different ways. So in the active configuration, the gadget sends the interrogation signal and receives it, while there are also methods where we can essentially leverage the existing signals in the environment. We can essentially rely on the ambient radio waves. And considering that most buildings in the US these days do have Wi-Fi, or I should say a lot of them, it is actually pretty common to be in the environment where we can harness radio waves that are already there. So that may help in the future to leverage that existing infrastructure so that we don't have to add a whole lot of hardware to be able to do this kind of sensing. So again, we're measuring cardiopulmonary motion on the torso, and we can pick up signals on the skin. We can also pick up the signals under the skin. It just depends on how the radar is implemented. The frequency of operation is pretty much anything between DC and light. So most of our work has been at frequencies between 2.4 gigahertz and 24 gigahertz, but we have done some work at higher and lower frequencies, and there are various trade-offs. Again, this is a non-contact technique. It works through floating and bedding. It can work through walls if it is designed for such operation. And we have measured rates at distances between 1 meter and up to close to 100 meters. So again, it just depends on how you configure your hardware. There are a lot of different options in terms of what sort of range we can expect. Sometimes we want a lot of range and sometimes we don't, right? If we want to minimize noise from other sources. So we have successfully extracted respiration rates and heart rates using this technique. What I'm showing you here is the first FDA-approved Doppler radar that we worked on with our first startup. And we have also extracted some more complicated parameters such as tidal volume and pulse pressure and sleep postures. So essentially based on the reflected signals, we can tell if the person is sleeping on their back or their side. And this is important for managing sleep apnea and other sleep disorders. So this is essentially showing you the testing setup, the human testing setup for the sleep apnea. As I mentioned, we have been able to actually recognize obstructive sleep apnea, and Victor currently has an NSF project to take that further. We have been able to isolate signatures from multiple subjects, and we have also been able to provide identity authentication for the subjects that we are monitoring. So that's a lot of health related work. But we're now focusing more on the infrastructure for smart buildings. So you know that in smart buildings, there are all sorts of gadgets that are already installed. Wireless networks are very common. Imaging devices are also very common. The question is, can we leverage that? And if we're able to actually use the devices that are out there without burdening occupants in any way, without asking them to opt in or without asking them to wear any devices, if there is less burden, there is a higher chance of success. Right? So the other things that occupants may be interested in are their privacy, right? So which is the reason why video cameras are not always the best choice for monitoring, although there are systems that use some video cameras. And they also are interested or concerned about security, right? About the security of their data and also about the security of buildings. And then in terms of infrastructure, again, if we're able to provide solutions at lower cost, solutions that can leverage what is already in the environment without actually having to drill holes and install new hardware, then again, there is a higher chance of adoption. So this is why we think, these are the reasons why we believe that our remote sensing technology is a good fit, right? And I'll tell you next about what we're doing in the intelligent occupancy sensing. So first of all, through human presence detection. And what I mean by that is making sure that when presence is detected, that it is actually really a person and not a moving curtain or a fan or a pet or just airflow from air conditioning. And also when the sensor is saying that nobody's there, that there's really nobody there and not just a person working in their computer and not moving enough for the sensors to pick them up. We are also interested in occupant count, and the reason for that is essentially HVAC control, because the space needs to be conditioned very differently if there are only a handful of people in space versus if the space is occupied at full capacity. And this is actually something we started looking before COVID, but it has perhaps become even more relevant now as a lot more people are working remotely, and actually occupancy patterns are less predictable than they used to be. We also looked at the activity assessment, essentially looking at how much are people moving and how much do they just sit around. We are getting into comfort and stress assessment because we're measuring physiology. We believe that there is a potential to actually tell if people are comfortable, stressed, and how they respond to environmental quality. And I mentioned previously authentication for health monitoring, essentially making sure that we're measuring the same person. And in building applications, the angle here is similar, right? Making sure that whoever is using the computer is the owner of that computer, or making sure whoever is using a certain lab facility is supposed to be there. So starting by through presence and count. The basic motivation here is to reduce energy waste. So the current occupancy sensors mostly use passive infrared and ultrasound technology. But about 80% of all occupancy sensors that are deployed in buildings are passive infrared sensors. And they're really great in terms of being very inexpensive and detecting people when there is large motion. So if you walk into the room, walk out of the room, sensors are going to be able to detect that, but passive infrared sensors. But when you sit down into your computer, after a while, lights may turn off. You may be familiar with this, where you need to move around, wave your hands for the right lights to turn on. Now, it's not necessarily bad that you have to walk around or move about every once in a while. That's actually, from the health perspective, a good thing to do. But the problem is the occupants get annoyed when they have to do this. And then what happens is they either set long delays on the sensors. So when the sensor actually says that nobody's there, the lights are not turned off, and the delay maybe half an hour, maybe longer, or they disable the sensors completely. So this is actually a fairly common complaint. And when that happens, then the savings that we get due to output of these occupancy sensors are greatly diminished. So essentially that's the potential that's not realized. Now, what we are working on is detecting presence based on vital signs, so based on respiration, based on heart rate. So there is no question if the person is there or not. And actually, our technique has advantages when people are not moving. When people are not moving, we can get a lot of information. When people are moving, it's pretty easy to tell, again, with other technologies, that there is motion. But we can actually discern that motion and figure out, is it a person, is it a curtain? Is it something else? And then, as I mentioned, count is another piece that we're interested in here. So current occupancy sensors are mostly installed, almost exclusively installed to control lighting. There is not a whole lot out there to control HVAC beyond setting thermostats at some predetermined points, or perhaps by using scheduling, right? But HVAC is typically not controlled based on occupancy, or at least not yet. So that's something that we're also looking to hopefully change in the future. And then there are other interesting parameters that can be inferred once we have data on the occupancy. For example, we were approached by an architecture firm. They were interested if their space, if the design for their space was effective in terms of improving the flow of people. And they asked us to essentially count people in certain areas to essentially determine if their architectural design operated as intended. Now, that was right before COVID started, so we haven't had a chance to test that, but that's another possible direction for this type of work. So I want to share with you some of the testing that we have done, in some of it at spaces at UH and some of it outside of UH. So we did testing in buildings that are nicknamed FROG buildings. That stands for Flexible Response to Ongoing Growth. So these are essentially configurable kits buildings. The area that we're monitoring there is about 1,400 square feet, and we're monitoring that with a single sensor. So our sensor is right here. You can't see it. It is very small, but we did monitoring there for several months. And the first order of business was to prove that our sensors were indeed better than the conventional occupancy sensors. So we ran the testing concurrently with passive infrared and with ultrasound sensor. So I'm showing you two instances here where we can clearly do better. So the image on the left is blurry because that's all we got permission to collect. So we had to essentially blur the video camera to preserve privacy of the occupants. And it is no small task to actually identify people in these blurred images and count them. So that's kind of an offshoot of our work that is also ongoing. But in this case, only instructor is present during recess, and the conventional sensors, so in this area here, are essentially saying there's nobody there, whereas our sensor is clearly identifying a presence. Now, another interesting thing that happens is fans actually do set off passive infrared sensors. And then the other thing that sets them off are changes in temperature. So changes in cloud cover or shading that is also related to fans actually sets off a passive infrared sensor. So this is actually one instance that conventional sensors are saying that somebody's there, and we know that that's not the case. We have done some controlled experiments for occupant count where we had like one person enter the room at a time, and we arranged them neatly, and then the output of our algorithms looked pretty good. When we do it in an uncontrolled environment, so this is another picture from the front building here at the bottom, there were, I think, more than, this was the case with 25 or 30 people, I forget. We have some success, so this is very early data that hasn't been published yet. So this is essentially what we're working on now, figuring out how many people are there when they're in all sorts of different orientations. And we may not even know ahead of time how the room is configured, because the frog buildings are, the furniture inside is movable. So sometimes it is in classroom configuration and sometimes people are sitting around the room. So we don't know that ahead of time. We have done occupancy monitoring in another building in UH called Sakamaki Hall. And the purpose of this was to determine if people are really there, because our facilities office gets requests to turn on AC over the weekend and pretty much running 24/7. And they're not happy about it because we have huge electricity bill to pay. And they asked us to look into how much is that space actually being utilized. So we installed sensors in 6 locations and did monitoring over 6 months. Unfortunately, again, this was mostly during COVID. But the occupancy pattern that you see at the bottom is kind of very typical, right? So it starts somewhere around 7 a.m. and then we see this dip here around lunchtime. And then there's a less occupancy in the afternoon than what we see in the morning. And this is averaged over all days of the week and all months. So if we break it down by different days, different months, then there is more interesting information in the data to be extracted. So the other area that we were interested in is this activity recognition again. And can we tell the difference between a person and a mechanical target? And these signatures are very distinct. So when the human subject is just sitting there, this is the sort of output that we get from our sensors. When people are walking, it looks very different. So that's pretty easy to differentiate. If they're moving more with higher velocity, we can differentiate that. Now, there's not a whole lot of that in the building, right? Unless it's some sort of a gym. But in most cases, people are either going to be sitting or walking. But the important thing is, again, we can distinguish mechanical targets from human subjects. So the fan looks very different from a person because the frequency at which the fan is moving is constant, because physiological parameters vary in time. Okay, so now how is this related to thermal comfort, guys? So it is related because physiology does hold clues as to how people feel. And there have been efforts to assess thermal comfort non-invasively at a distance. So most notably, there has been work to use skin temperature using infrared cameras. Skin temperature is a proxy, and it may be a very useful proxy, but we can likely get more accurate information by actually looking at physiological parameters. So there has been some work published, not a whole lot, on relating heart rate variability with comfort. And when people are not comfortable, this ratio of low frequency to high frequency in their heart rate spectrum increases. And that seems to be consistent at cold and warm temperatures. So this is something that we want to look into next. So Doppler radar is suitable for heart rate variability analysis because for heart rate variability, you essentially need two things. You need to have respiratory pattern, and you need to know how heart rate varies in time. And we're getting both heart and respiration with our technique. So we have started doing some testing at NSF Lisa Center at Rensselaer Polytechnic. So this is the picture showing your installation. So sensors installed at the ceiling. The room size here is about 30 feet by 10 feet. And what this diagram is showing you here is instances where we can pick up respiration, which is pretty much anywhere in the room. And we're also able to pick up heart at quite a few locations. And we're now working on fine-tuning it to make sure that heart is there. And I'm getting lots of hearts, so that means I need to speed up. Okay, so authentication. Again, this is something that is done that we have done based on respiratory and heart parameters. So these physiological parameters, they're kind of like a fingerprint, maybe not quite as unique, but people do breathe differently, and their heart rate variability also is a unique signature. So that's another interesting area to look into. Another area that we think is very promising, especially with respect to not having to drill holes in walls and install new hardware, is leveraging signals that are in the environment. And we have done some work that is actually being presented this week in ENBC conference remotely. And we have essentially used wireless comlink in 24 gigahertz to do this kind of testing. And the motivation here was to check if we can test respiratory rates that are consistent with COVID. That may help with pre-screening. Okay, so the future directions. So the one project that we're really excited about that has just started is to adapt indoor environmental parameters based on physiology that we sense to promote healing. This is a collaborative project with Arizona State and Drexel, and testing will be done at CHOP. And the unique aspect of that project is that we're talking about hospital rooms. There's probably most of the time there's going to be one person in there, perhaps two or three. So that should help us get started because we're not separating signatures from a lot of different people. But we would like to move into the direction of being able to do that for larger, higher occupant counts, such as classrooms, conference rooms, and other settings. And we have been working on several different techniques to isolate signatures from multiple people. Now, I don't know how to adjust environmental parameters when one person is cold and the other one is when one is hot and one is cold, but that's an interesting research question for the future. I want to mention also a little bit about our tech transfer work. So, it has been a pain in the neck to work through conflict of interest management with the university and, make sure that all of that is taken care of properly. But I feel like that it has been very important, especially in Hawaii, because we were able to create jobs for 11 of our PhD and MS grads over the years. And we also trained our students in taking research out of the lab and essentially what it means to actually make something that really works and in entrepreneurship. And some of them have spun companies of their own. And there's been a paradigm shift. So we started this in 2007. And since then, faculty are now actually officially allowed to use their lab facilities and their laptops for their startups. So I don't have to pretend anymore that I'm using two different laptops. So I'd like to acknowledge the support from, so most of this work has been funded by NSF and some of it by NIH. And I want to thank you all for your attention today.
Thank you, Olga. We thank you, and it's so nice to see you here. Wish it was in person, and I'll take you up on your offer to come to Hawaii. So we have a number of questions. We won't be able to go over all of them, but you are going to have access to reply to them in Kai Storm. One question or two questions I can combine. One is related to stress and what could be some of the other health assessments to be done by this technology or using this technology, as well as what is needed for this technology to be used for a wide spectrum of well-being understanding. So I think these two questions are both asking, like, what can we use this technology for in terms of health and well-being?
Right. Well, if we're just focusing on health, then one application that I mentioned is sleep monitoring, right? So any application where you want to monitor people without putting any sensors on them. So it is suitable actually for home monitoring in general, right? Sleep monitoring is one application where we have easy access in terms of we know exactly where people are. And it's not difficult to discern who's who, because at most they're going to perhaps, two people there and a pet, right? So there's not a whole lot of signal separation. We can do monitoring throughout the day as people move around their home as well. So this is one application that has come up is elderly monitoring, right? Monitoring their movement patterns, predicting falls, that sort of thing, right? Now, as far as diagnostics, looking at what do these respiratory and heart signatures means, I mentioned COVID screening. So I wouldn't say COVID detection, but flagging people that perhaps should get a PCR test is something that we can do, because changes in respiratory rate are actually in the early indicators. So they happen before there is increase in temperature. So we can actually check it before temperature screening would flag it. And then there are a number of other conditions. So, monitoring people who have any kind of respiratory disease, monitoring people who have any kind of cardiovascular condition, right? So essentially what we're good at is monitoring changes over time and correlating changes in respiration activity and changes in heartbeat, right? So most of the other technologies, they focus on one on the other. And most of it is really focused, like smart watches, you're going to get your heart rate just fine. But there are not a whole lot of sensors that get information on respiration. So that's really where our strength is.
That's great. And again, we have many questions from understanding people's individual needs to energy consumption of the technology to privacy issues. But since we're running out of time, I will encourage you and ask you to go and comment on these questions and in an offline fashion. Thank you so much, Olga, for the great presentation. It's very, very interesting.
Well, thank you for inviting me.